Hi dear students, so today we have come with a new video and I think you all are well in this difficult situation. So in the previous lecture we have discussed about capacitors, right? In previous two lectures we have learned about what is capacitor, how it works, how we can able to combine it. Now today we'll learn a new thing, that is dielectrics in capacitor. Dielectrics in capacitor. So whenever we are writing this whole heading capacitor, it is okay, but what is this dielectrics, that we will learn today. Okay, but before learning that thing, one thing it will come to our mind, that what is the need of a substance in a capacitor. What is capacitor? If I'm asking to you, you all know that if two metal conductors are kept at a certain distance, it will form a electrical equipment, okay, and that is known as capacitor. How it works? Now when we have connect with it with a cell, then in one portion or in one plate positive charges will induced, in another plate negative charges will induced, and by that way what we have done there, now by that way we just want to store the charges. Our intention is that if I store the charges, then for certain instrument where much amount of current is needed at the time of starting, I can easily supply that current. So that capacitor will be much effective, which can able to store much charges. That capacitor will be effective, which can store much charges, which will store much charges. There capacitance, that is also one property of a conductor by which it can able to store the charges. So capacitance will be more, but we have seen here there is a problem. If we have kept a gap between the two metal plates, what is the problem? Here you see, as there is a positive charge and here is the negative. So here this is a direction of electric field is acting this way. Okay, so as there is no substance in between them, so the electric field is very strong. Then you may ask, sir, if electric field is strong, then what is the problem? Problem is that if electric field between the plates are strong, is strong, okay, is strong, then the potential difference is also strong, because we have learned that dV equals to minus of E dot dr, okay, or V equals to integration of E dot dr. So more the electric field, more the potential. Then you may ask, sir, more the potential, then what is the problem with us? Yes, there is a problem. We have learned that capacitance C equals to Q by V. So you see, if V is more, then our capacitance will be decreased because V is in denominator. So our target is to store much amount of charges here. But what we have seen, that if no substance is kept in between the gap between the two plates, then what will happen? Then the electric field will strong, and if the electric field is strong, the potential difference, okay, that will also be strong, and if the potential difference is strong, then the capacitance will be decreased. So our target is what? Number one, we want to decrease electric field, right? Because if electric field is decreased by us, then the potential is automatically decreased, and if the potential difference is decreased, automatically the capacitance will be increased. And our target to form a capacitor is to make the charge stored more. For that reason, the capacitance C, that will be more. Okay, so how the electric field will be decreased? To decrease the electric field, to decrease the electric field, dielectric substance is introduced between the plates. Now you might be asking, sir, we don't know dielectrics. So dielectrics is introduced, that we have learned, but how dielectric decrease the electric field, how we can able to understand it? Yes, so for that reason, today's topic is all about dielectrics. Though I have made the heading dielectrics in capacitor, definitely that we will learn. But before that, we have to learn the dielectric. What is the dielectric first? And then we'll go for dielectrics in capacitor. But what is the need of dielectrics and capacitor? What is the use of dielectrics in capacitor? I think this idea is clear through this part. Okay, next we will go for dielectrics. Okay. So I have already told we have to learn about dielectrics. What is it? If I go by the definition of the dielectrics, it tells that it is a substance, which doesn't allow any charges to move through it, but it will show effect in an external electric field, and it is polarized. Okay, again a new term has come. Let's see step by step. We have to discuss all the parts we have to learn in dielectrics. Let's see what it is told. It is a substance which doesn't allow any charges to move through it. By read that statement, it is clear that dielectrics are nothing but insulator. Dielectrics are nothing but insulator. So if anything doesn't allow charges to move through it, so it is insulator, no doubt about it. But all the insulators are not dielectric. Okay, why? Because the next thing it is told, it will show an effect in an external electric field. So dielectrics are such kind of insulator which will show effect. What is the effect? That effect is known as polarization. I have told now in electric field, and it is polarized. So this effect is known as polarization. What is it? Everything we will discuss. Okay. So this type of substance is dielectric. If I am asking you the example of dielectrics, many more examples are there. That's like wax, water, glass, mica. See, all that substances I have written here, these are insulator. Okay, but in external field, they have behaved just like a polarized substance. Why? How? Let's see. But before going on polarization, we have to learn how many types of dielectrics are there. So when we are talking about the types of dielectrics, there are two kinds of dielectrics are there. Number one, that is known as polar dielectrics. Polar dielectrics. And number two, non-polar dielectrics. What is it? What is polar and non-polar? So before learning about polar and non-polar, I am just taking to you in class 5, 6 or 7, this classes. In this class, we have learned that all the substances are made by molecule. If I am not wrong, you have learned it in class 6. Okay. So all the substances are made by molecules. So if I am talking about a molecule, so the molecule, it may be monoatomic, it may be diatomic, it can be triatomic, okay, but it can be polyatomic. So here, when a molecules are formed, there are several kind of formations are there, several kind of molecules are there. If I am talking about oxygen, nitrogen, hydrogen, this type of molecules are formed by adding two same kind of atoms. Okay, so here, whenever this situation is gone, in that case you see oxygen plus oxygen, they are adding and giving a O2. Same kind of substance. If we go inside it, inside the atom, we know there is electrons, there is proton inside the nucleus, neutron, etc. The things are there. Oxygen and oxygens are added because of a covalent bond is created between them. So here I am not discussing about the chemistry, so we will not go far beyond that. But here you see two same kinds of substance. So here also positive charge and negative charge is there in oxygen. Here also positive and negative charge is there. When it forms O2, so inside there is positive and negative charge, but in this charge they are just aligned in a same line. That means positive and negative, they are just aligned in same line. So we don't get any pole, as it is formed by two same kind of atoms. I'm repeating my word. So that's why the charge inside, the positive and negative charges, they are just aligned in one line. So we can say the center of mass of positive charge is aligned with center of mass of negative charge, and that's why we have not seen any pole. This type of dielectrics are known as non-polar dielectrics. Remember the name, non-polar. No pole is there. When it is happened? Now when the center of mass of positive charges coincide with the negative charges, with the center of mass of negative charges, that type of dielectrics are known as non-polar dielectrics. Why? Because I have already told that the positive and the negative, they are coincide. Total positive charge and total negative charge are coincide with each other. Coincide means as it collide with each other, then it will be neutral. No, it's not collide, and you know also it will definitely not collide, but the net line of charges will be same, and that's why no pole is created, and that's why it is called non-polar. Example, if I am talking about here, oxygen, nitrogen, methane, Okay, so this type of examples are there for non-polar dielectrics. Now you might be asking, sir, polar means in this molecules, so dielectrics are also made by molecules. So in these molecules, there will be a inbuilt pole is there. Just like if I'm talking about HCl, okay, if I'm talking about HCl, so here we have seen H plus and Cl minus. So the molecule in HCl, there is already a positive ion and negative ion. They have just kept at a certain distance. If I'm talking about H2O, I think you know the formation very well than me. Okay, I think there should be double bond or single bond. Forget about that. It is a bond. Okay, I'm not going with the number of bonds are there, so there will be a little bit of confusion. I think it's single bond. So here you see the negative charges are there in oxygen, and here there is positive charges. Okay. Oh, I have done. That's why the confusion has come. Oxygen and here is 2 hydrogen. Okay, here is plus, here is plus, here is 2 minus. Okay, so here you see inbuilt a pole is formed in this molecules, and that's why these are known as polar dielectrics. So we can write when the center of positive charges are not coincide with center of negative charges. These are known as polar dielectrics. Means you can say here positive and negative are just kept like this way. Positive is in one terminal, negative is in another terminal. So here if I am talking about the example, just like H2O, HCl, okay, CO2, this type of substance, or alcoholic substance CH3OH, methyl alcohol, this is also a polar dielectrics. Okay, so these are two different kinds of dielectrics are there. Number one, there is an inbuilt pole, that is positive and negative pole is there inside the molecule, and in non-polar dielectrics the pole is absent there, because here the positive charges, means the center of mass of the positive charges and center of mass of the negative charges are coincide with each other. Okay, now, okay, so I think the idea of dielectric is clear. Now we'll go for the effect of dielectrics in an external field. The effect of dielectrics in an external field. Let's see what it will be. Effect of dielectrics in an external field. Assume you have taken two plates. In one plate you have connected with the terminal of positive of a cell, so their positive charges are come, and one terminal you have connected with the negative, so negative charges will come. So this is a direction of electric field. Okay, and assume you have to put a dielectrics here. So which dielectric you have to take? First you take a non-polar dielectric. Okay, first we have taken a slab of dielectric which is non-polar. Okay, initially assume when there is no charges, in the plate, so we know the positive and negative charges are like this. They are just coincide in one vertical line. You can assume that positive and negative charges are just aligned in a vertical line, so net pole is 0. But whenever you have on the switch, okay, so we can do it in another diagram also. Assume here no charge is there. So if there is no charge, so there will align this way. Okay, no electric field. And now what you have done? You have taken the same setup and now you have switched on the connection. So what will happen? If you switch on the connection, there will be an external electric field is coming. So as there is an external electric field is coming, due to that there will an effect shown in dielectrics. What effect is shown? Now the effect we have seen here, that the positive charges should be attracted by the negative charges. The positive charges of this dielectrics should be attracted by the negative charges. So the positive charges will go in this side and negative charges will come in this side. Positive charges will go in this side, the negative charges will come in this side. So they will align like this way for a non-polar dielectrics. So initially there is no pole, but whenever you have kept it inside the external field, then we have seen a pole is created, positive and negative. A pole is created and that is called polarization. This is known as polarization. Polarization means pole formation, no pole to pole. But assume if I have taken a slab of polar dielectrics, so here from the first there is pole, from the first only there is pole, but whenever you have just put it inside the electric field, definitely the length of the pole will be increased because they have formed the pole in a very smaller area. But as we have kept here, the length of the pole will be increased. That means it is already polarized from the earlier. It is already polarized from earlier, but now the length of the pole is increased more for polar dielectrics. Okay, so how the two type of dielectrics behave in external field, that you have seen. So simple thing, in one word if I have told that if I put a dielectric substance inside the electric field, there will be polarization. That means the positive and negative charges, the center of positive and negative charges will just align exactly opposite to each other by making a certain distance between them, so that a separate poles are created. Okay, now you remember, whenever we have read dipole, I have told that what is the need of dipole, why we have read dipole, why we have calculated the dipole of electric field, the electric field of dipole, the potential of the dipole. The reason is that we want to do work with the dielectrics, and here you see the dipole is created. Two same kind of charges are exactly separated by a distance. Okay, any doubt? I think no. Now we have to see how electric field is reduced in the existence of dielectrics. Okay, so here we have to see the next thing, the reduction of external field due to the presence of dielectrics. Okay, how it occurs? So assume I have taken two plates. I have given charges to them. In one side positive, another side negative. Okay, no problems with that. We know. Okay, and whether we can take a polar or a non-polar dielectric slab here, there should be a polarization. If I take polar also, then the polarization will be more, and if I am taking a non-polar dielectric, then the polarization will be less, because for polar it is already a dipole, and due to the presence of electric field it is increased, and here non-polar, initially there is no dipole. Due to the presence of electric field, smaller polarization is created. Let's see. So as I have kept this, definitely the positive charges inside the dielectric, that will just align in this direction, because that will be attracted by the negative charges just aligned in the plate, and all the negative charges of the dielectric should be aligned in this direction. Okay. If I am talking about the direction of electric field, we know the direction of external electric field, that is denoted by EO, okay, or E0. So we can mention that E0 is external electric field. Okay, and due to it, what polarization is occurred? The pole has been formed, and in this case you see the direction of polarization is exactly opposite to the external electric field we have given. Here it is positive, but here a positive is in opposite direction. So this is, we can say, EP. What is EP? Now EP is not for eating. Okay, EP is electric field due to polarization. Okay, now what will be the resultant electric field then? Then resultant electric field. Okay, so resultant electric field will be, it is very clear that E is equals to E0 minus EP, because you see the direction is different. The direction of this two electric field, that is electric field due to external electric field and electric field due to polarization, they are exactly opposite with each other, so the resultant field is decreased. Now remember, the first thing I have told, that we just want to introduce a dielectric inside the two plates of capacitor. Our target is to reduce the electric field. You see here how we can able to reduce the electric field. Now the question has come, so is the reduction of this electric field is same for any material? No, definitely not. So it is different for different dielectrics. So how we can denote different dielectrics? We denote different dielectrics by dielectric constant. Okay, it is denoted by dielectric constant. See, we have already learned what is dielectric constant. What is dielectric constant? The dielectric constant is nothing but the ratio of external electric field to the reduced electric field, that is known as dielectric constant K. Now you might be asking, sir, when we have learned this thing? We have learned it in the first chapter. Here it is coming, epsilon by epsilon naught equals to K, that epsilon equals to epsilon naught into K, where epsilon is permittivity of a dielectric substance, epsilon naught is permittivity in free space. Okay, and K is the dielectric constant, which is denoted by another name, that is relative permittivity. So this is a dielectric constant. So by this statement we can say that dielectric constant K equals to E0 by E0 minus EP equals to K. that is the dielectric constant. E0 minus EP means E, that is the resultant electric field or reduced electric field we have seen here. And depending on the value of K, we can say that what will be the resultant electric field, because depending on the value of K, how much polarization will occur, that we can understand. How much polarization will be occurred, that we can understand by the value of K. Okay, so this is dielectric constant and reduction of electric field. I think this is clear enough. Now, as we are talking about polarization, that is a new term for you. And now we have to learn how this polarization we can able to calculate, that how much this positive and negative charges will coming and make a separation between them. That depends on the property. So what will be that property and how we can measure the polarization, that we have to learn in the next part, that is polarization density. Okay, polarization density. Let's see. Okay, I hope this part we have discussed here, so that doesn't seems to be too hard. Okay, just try to understand. Okay, then I think it will be very much interesting for you. Don't think that what is E, A, B, C, D. No, it's not English class. I'm not making you learn some alphabets here. I just want to try to make that things very easy. Okay, and yes, hope you can able to understand. Polarization density. What is polarization density? It tells that polarization density is dipole moment of a dielectric substance per unit volume. Dipole moment of a dielectric substance per unit volume. What is it? Assume this is a dielectric slab is given to you. This is two plates. Here it is positive. Here it is negative. Assume the length, you can say the breadth of the dielectric slab, it is D. Okay, and the area covered. Okay, so we have written here the area is equals to A of the dielectric slab, and due to the presence of external electric field, we know here in two terminal the opposite charges will be generated. Assume this opposite charge is generated due to polarization. These charges are generated due to polarization. So the value of the charges are QP. So if it is QP, it should be minus of QP. Okay. So from here, if I want to find out the dipole moment, so dipole moment is what? Dipole moment is charge into distance between them. So here the charge we have assumed, that is QP. So it is QP into D, because the distance between them is D. And if I am talking about the polarization density, that is equals to sigma P. So sigma P, okay, on some book polarization density it can be denoted by P, not sigma P. Forget about sigma P. Polarization density actually it is denoted by P. It is a vector quantity. Polarization density P. So this P equals to dipole moment by volume as per the definition. So dipole moment is QP into D. What is volume? Volume, if the area is A and distance is D, so it is A into D. So cancel D here. It is QP by A. it is QP by A. So charge per unit area, that is the polarization density. But we know the charge per unit area that can be denoted by sigma p also. Charge per unit area that can be denoted by sigma p. Okay, so we can say that polarization density is equal to the charge per unit area of a dielectric substance. Charge per unit area of a dielectric substance. Okay, now the next thing we can learn from here, that is the charge per unit area. Another very important thing we can do here, that is susceptibility, or we can mention it is dielectric susceptibility. What is it? It is also one kind of property of a dielectric substance by which we can able to understand that how it can be polarized. Okay, there are more physical significance of dielectric susceptibility is there, but that I will not discuss here. It will be discussed in the next chapter whenever we have learned magnetic substances. There this susceptibility part will be discussed more, but now you have to learn it is one property of the dielectric substance. Okay, let's see it. Dielectric susceptibility. Dielectric susceptibility. What is it? Dielectric ability, which is denoted by, okay, which is denoted by a very interesting symbol that is known as chi. Chi. Okay, but the spelling of chi is this chi. Don't, it is chi. You don't think that it is chi. No, it is pronunciation. The pronunciation of this symbol is chi. Okay, so dielectric susceptibility is what? Polarizing density. What we have just calculated, that polarization density P. It depends, if I am talking about on which thing it depends, here it is told it depends on two things. Number one, the electric field, the external electric field we have given. Polarization density is directly proportional to the external electric field we have given. But when we have to talking about this external electric field, so here the electric field is reduced, so we can say polarization is directly proportional to the resultant electric field. P is proportional to E. Another one, P is proportional to the medium. Now the problem has run, by which property we have to represent the medium? Is there any property to represent the medium? Yes, we are having permittivity. So epsilon naught we have to take, that is permittivity in free space. So you may ask that why we are taking free space? Because we have already taken a dielectric. Okay, and when the dielectric is taken in a medium, so that medium should be the outer medium only. What will be the another thing? Okay, so P is proportional to E and P is proportional to epsilon naught. If I written together, P is proportional to epsilon naught E. So we need a constant. What constant we have to take here? That is chi. Chi epsilon naught into E. Chi epsilon naught into E. That is the measurement of polarization or polarization density. Now this calculation, whatever I have shown here, it is not coming whatever we have shown it directly. It is coming mainly experimentally. So that's why I have told, don't be panic with it from where it has come. Okay, you have to remember that P equals to chi epsilon naught E. Later you will get it in magnetic substance. Okay, so if I want to define chi, so chi equals to P by epsilon naught E. So what we can say, chi It is the ratio of polarization density to epsilon naught times resultant electric field. Okay, so that is known as chi, and you have to remember that chi, it is also a number. Chi, it is also a number, so its dimension is 1. So it shouldn't make any sense with the dimensions or unit about that thing. So the unit of P and the unit of epsilon naught E should be same. Okay, so that is dielectric susceptibility. Now we'll go for the last thing of this portion we have discussed, that is the relation between dielectric constant and susceptibility. The relation between dielectric constant and susceptibility. So dielectric constant we denote it by K, and susceptibility it is denoted by chi. So the relation between K and chi, that is our target. We have seen here that E, resultant electric field, E equals to E0 minus EP. Resultant electric field E equals to E0 minus EP, that we have just defined just now. So E0, the external electric field, E0 is equals to sigma by epsilon naught. Now you may ask, sir, from where this sigma by epsilon naught has come? I will make you remember that whenever we have to find the electric field of a parallel plate capacitor, so for this plate we have written sigma by epsilon naught. For this plate, as it is opposite, so it is minus sigma by epsilon naught. So resultant sigma by epsilon naught minus sigma by, it is 2 epsilon naught. Sigma by 2 epsilon naught minus sigma by 2 epsilon naught. So it will coming sigma by epsilon naught. If you have forget it, go to the chapter 1 where we have finding out the capacitance of a parallel plate capacitor. There we have found the electric field of a parallel plate capacitor, and it is sigma by epsilon naught. Okay, just see the video again, then you can be understood. So epsilon naught, E0 equals to sigma by epsilon naught. So similarly we can write EP. So EP, that is electric field due to polarization. So EP, whenever we have seen here, so here it should be sigma P by epsilon naught. What is sigma P? Now sigma P is charge density, charge per unit area in a dielectric. We have seen it earlier. Okay, so here we can write E0 equals to sigma by epsilon naught, and it is sigma P by epsilon naught. We have done one more thing, that is sigma P equals to P. That also is proved. In the previous part we have shown that sigma P, that is charge per unit area, is equals to polarization density. We have just proved polarization density equals to dipole moment per volume, and from there we have seen it is equals to charge per unit area. So it is sigma p. Instead of it we can write sigma by epsilon minus, instead of p is sigma p, we can write p by epsilon naught. Okay, and here epsilon naught, so this one we can write E naught. Sigma by epsilon, it can be E naught. So to make you understand that E naught equals to sigma by epsilon naught and EP equals to sigma p by epsilon naught, I have done this. So P, what is the value of P? The value of P equals to epsilon naught chi into E. Epsilon naught chi into E, that we have just done in the previous part. Okay, so now epsilon cancel out, take this portion here. So here it is E, if you take a common, 1 plus chi into E equals to E naught, and here 1 plus chi, E to I have taken common already, 1 plus chi is equals to E naught by E, and we know E naught by E equals to K, that is dielectric constant. So K equals to 1 plus chi, that is the relation. K equals to 1 plus chi, that is dielectric constant equals to 1 plus dielectric susceptibility. Okay, maybe this in this portion something I have shown you, maybe it is little bit of difficult for you because I have taken it from the previous video, because that's why I have told what videos I have sent you have to see properly. If you skip one video, then you cannot able to understand from where E naught equals to sigma by epsilon naught. So if you not understand this step, it will be difficult to write sigma p equals to sigma p by epsilon naught. Okay, EP equals to sigma p by epsilon naught. So don't skip any portion. See the whole video and all the videos I have given, and then I think you can able to understand. From here some numericals are come in board, it can come, but the chance is maximum in the competitive exam, that is NEET JEE. Okay, many more questions are coming from this dielectric constants and susceptibility. Okay, see that portion, I think it will be helpful for you. Thank you.